B2, this question is about atomic spectra. So in diagram 1 shows some of the energy levels of the hydrogen atom. Diagram 2 is a representation of part of the emission spectrum of the atomic hydrogen. The lines shown represent the transitions involving the minus 3.4 eV value. So here we have the minus 3.4 value, and this is an emission spectrum. So we have that your electrons will drop down, say from there to there. The electron will drop down and it will go to a lower energy state and therefore give out a photon of light. And that photon of light, the wavelength of that will correspond to the energy difference between these two. So let's have a look at the question. It says, deduce that the energy of the photon of wavelength 658 nanometers is 1.89 eV. Well, we have this formula here which looks at the energy of a photon. So we need to use that. We also need to use our formula that C is equal to frequency times wavelength, because we are given our frequencies here, well, in terms of wavelengths, so we need to use wavelength. So frequency is equal to the speed of light divided by lambda, and so I can put that into this equation here and I get E is equal to h c over lambda. So we're going to use that. So we're going to put into that equation there hc over lambda. So this is h is 6.63 times 10 to the negative 34 times the speed of light, which is 3 times 10 to the 8, divided by 658, and that's nanometers. So the nano is 10 to the minus 9, so times 10 to the negative 9. So we have that, and when we calculate that, that is 3.02 times 10 to the negative 19, and your answer there would be in joules. Now, we want ours in EV, so to convert joules into EV, I have to divide. I must divide by 1.6. Sorry, I must divide by 1.6 times 10 to the negative 19. So my energy in EV then would be 3.02 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19. And when I get that, I get 1.89 eV. Now, another way that we could have calculated this without having to do much in the way of calculation, although this is important that you can do this over here, is that because this is the longest wavelength, it must be the lowest energy. And therefore, because it's the lowest frequency, because your C is equal to frequency times wavelength. So if you've got a high or a long wavelength, your frequency must correspondingly be low, and because your energy is proportional to your frequency, you've got your lowest energy. So this must be, because we're dealing with this minus 3.40 eV, it must be this one over here, which will be the lowest energy difference. So if I take 3.40 minus 1.51, I get my 1.89 eV. So you'd need to have explained that, but you could really have just done that. That would be probably an easier way to go. Then it says, on diagram 1, draw an arrow to show the electron transition between energy levels that give rise to the emission of a photon of wavelength 6.58 nanometers. Label this arrow with the letter A. On diagram 1, draw arrows to show the electron transitions between energy levels that give rise to the emission of photons of wavelengths 488, 435, and 411, and label these errors as B, C, and D. So we're going to have then for each one of these as we go, because let's start with the first one over here, where we need to label A. So for this one over here, as we said, it would be this one here. This would be A, because this is your longest wavelength, therefore the smallest energy difference. Now 488 must be the next longest wavelength, and therefore the next smallest energy. So this would be B, C, and D, like that. Okay, and then the question also goes on with C. I'll just stay where I am here, but I'll just read the question to you. It says, explain why the lines in the emission spectrum of the atomic hydrogen shown in diagram 2, this over here, become closer and closer as the wavelength of the emitted photon decreases. Well, the energy differences here, the differences decrease as the wavelength decreases. So because here we have an energy difference, for instance, between C and D, we're going to have a smaller difference. It's going to be a smaller difference than between, for instance, C and B. That difference between those two. So because the difference in energies is going to be less, we're going to have a difference in the wavelength is going to become less. So these are going to become closer and closer together.